Hello, students, welcome. Have you ever wondered what happens inside a balloon when you heat it up? It inflates. But why? Well, it all comes down to gas laws. Gases, like the air inside the balloon, follow specific rules when pressure, volume, or temperature change. It's not just random, there's a pattern to how gases behave, and these patterns are governed by the three major gas laws. These laws help us predict how gases will respond to changes around them. So, when you heat up a gas, like the air in a tire or a balloon, the molecules inside move faster, pushing against the walls harder. And if you press down on a gas, it shrinks, the particles get squeezed together. This is chemistry in action. From the weather forecast to cooking, understanding these gas laws is essential for solving all kinds of real world problems. Now, let's talk about Boyle's law. Imagine you're at the beach with an inflatable pool toy. As you press down on it, what happens? The air inside gets compressed, and the toy shrinks. That's Boyle's law at play. It says that if you keep the temperature of a gas constant, the volume will decrease as the pressure increases, and vice versa. Simply put, pressure and volume have an inverse relationship. You can remember this by thinking of a balloon. The harder you squeeze it, the smaller it gets. Mathematically, Boyle's law can be written as pressure P multiplied by volume V equals a constant. In other words, P times V equals constant. Here, P represents pressure and V represents volume. If the pressure goes up, the volume goes down, and if the pressure goes down, the volume goes up. So, in your bike tire, as you inflate it, the volume increases as the pressure from the pump pushes the air in. Let's now turn to Charles' law. Have you ever noticed how a balloon expands when you leave it in a hot car? This happens because gases expand when they're heated. Charles' law explains this perfectly. It states that the volume of a gas is directly proportional to its temperature as long as the pressure stays constant. In other words, the hotter the gas gets, the more it expands. The mathematical expression for this is volume, V, is directly proportional to temperature, T, or you can write it as V1 divided by T1 equals V2 divided by T2, where T1 and T2 represent the initial and final temperatures in Kelvin, and V1 and V2 represent the initial and final volumes. So, if you heat a gas, the particles move faster, spread out, and the gas takes up more space. You've seen this when you've watched air expand in a hot air balloon, which relies on this law to lift off the ground. Now, what happens when both pressure and temperature change? That's where the combined gas law comes in. This law combines Boyle's and Charles' laws into one equation, making it easier to solve more complex problems. The combined gas law is written as P1 multiplied by V1 divided by T1 equals P2 multiplied by V2 divided by T2. This equation tells us that when both pressure and temperature change at the same time, we can still predict the final conditions of the gas. Imagine heating a can of soda. The air inside the can will expand as it warms up, but if you also squeeze the can, you'll change the pressure. This combined law helps us calculate how the soda can will behave when both of these factors change. Moving on to a very useful concept in chemistry, standard temperature and pressure, or STP. STP is a reference point that allows us to compare the behavior of different gases. At STP, the temperature is 0 degrees Celsius 273 K and the pressure is 1 atmosphere 760 millimeters Hg. This standardization is crucial because gases behave differently at different temperatures and pressures. For instance, we know that at STP, 1 mole of gas occupies 22.4 liters. That's a handy fact when you're working with gas volumes in your lab experiments or even in industries like food packaging, where gases are used to preserve products. Let's now take all the gas laws we've discussed and put them into one neat package, the ideal gas law. This law combines everything we've learned about gases and puts it into one equation, P multiplied by V equals N multiplied by R multiplied by T. Here, P is pressure, V is volume, N is the number of moles of gas, R is the ideal gas constant, and T is the temperature in Kelvin. This equation works for an ideal gas, a gas that follows all these laws perfectly. While real gases don't behave quite perfectly, the ideal gas law is a great approximation and helps us solve a wide range of problems in both the classroom and the real world, from weather predictions to designing engines. Let's look at an example now where we apply the ideal gas law. Suppose we have a gas at a known pressure, volume, and temperature, and we need to find the volume of the gas when the pressure and temperature change. Here's how we do it. First, we write down the given values for pressure, volume, and temperature. Then, we plug these values into the ideal gas law equation P multiplied by V equals N multiplied by R multiplied by T. Let's say we know the gas is in a 2-liter container at 1 atmosphere pressure and 300 K. We want to find the new volume when the temperature rises to 350 K at the same pressure. By rearranging the equation, we can solve for the new volume. This is how engineers calculate the volume changes in car engines, gas cylinders, and even weather systems. Here are the key takeaways about gas laws. Gas laws explain how gases behave under different conditions of pressure, volume, and temperature. According to Boyle's law, the product of pressure and volume remains constant at constant temperature. Charles' law states that volume is directly proportional to temperature when pressure is constant. The combined gas law and the ideal gas law bring these relationships together to handle more complex scenarios. And finally, always remember to use the correct units and express temperature in Kelvin for accurate calculations.